Hi students, in the second video for online lecture 4, we are now going to talk about two very important experiments that are going to show just how important energy and our photons really are. So the first experiment we're going to talk about was when Max Planck heated solids and was trying to look at the radiation that was emitted. This was done in the 1900s. Many of you might know the name Max Planck because of the scientific institutes that are created all throughout Europe that are going to be some of the best research in the world. So what happens is that when you heat a solid, they emit electromagnetic radiation over a wide range of wavelengths. You have seen this. If I were to heat a metal, you will typically see it turn orange, and then maybe a yellow, and then eventually a white, because it is going to be so hot that it is emitting all of the visible wavelengths. But those aren't the only wavelengths that are actually being emitted. There might be some infrared, there might be some UV, but how do we determine all of that energy? Well, the radiant energy emitted by this object at a certain temperature depends on the wavelength. So the interesting part is this is the first time we are tying wavelength, which was already previously tied to frequency, now to energy of the emitted light. So now what is happening is saying that energy, the light that we emit, can be and is now packaged in little discrete units. This is the first time that we are going to use the word quantum. So now we are starting to go into what we commonly know as quantum mechanics. How does our quantum actually work? How does light work? So what Planck actually came up with is known as the Planck equation. That is E, the energy of our discrete units, the quantum, is equal to H, which we know is Planck's constant. If you come up with the equation, you should be able to name it after yourself. So the Planck's constant is equal to 6.63 times 10 to the minus 34th joules times seconds. This is because we are going to take Planck's constant, h, and multiply it by our frequency. So we are going to have a frequency in reciprocal seconds. Planck's constant has seconds. So this means that we are just going to be left with the joule, and now we have energy. So finally, in this example, we are able to tie all of our electromagnetic spectrum to the energy in which it emits. The other thing that's very important in here is that if we look at our frequency and our energy, they are directly proportional based off of a constant. The higher the frequency, the higher the energy. But there's a slight problem in here, and that is we've already had our frequency tied to our wavelength. Another example in which we typically can put two equations together, those equations being our C equals our lambda nu, we can take our nu's from both of these equations and set them equal to each other. This is going to give us the combined Planck form, which says that the energy of our photon is equal to hc over lambda. This is going to be an incredibly useful equation for us, especially if you are given the wavelength. If you're given frequency, use E equals h nu, but if you're given wavelength, as you'll see here in the next couple of examples, you want to use the combined form because it is using the ideas of the electromagnetic spectrum radiation equation and our Planck equation that you see here. So let's try a couple of examples. Calculate the energy in joules. First, let's look at part A, a single photon with a wavelength of 5.0 times 10 to the 4th nanometers. This is in the infrared region. So as you can see here, we have wavelengths, so we want to use the ideas of our E equals hc over lambda. So one of the things that we have an issue with first is that our wavelength is not in the appropriate units. We're in nanometers. We must go to meters. So what we want to do with this value is state that we want to go from our nanometers to our meters. So 1 nanometer is going to be 10 to the minus 9th meters. So if I do this math, you'll see that I get 5.00 times 10 to the minus 5th meters. This has now become a useful wavelength for this equation. So let us go ahead and start plugging in our known values. We have our H, which is 6.63 times 10 to the minus 34th joules times seconds. We need our C constant, which we had in our last video, so that is 2.998 times 10 to the 8th meters per second. And finally, we will now go and get our wavelength, which we calculated previously as 5.00 times 10 to the minus 5th meters. So notice that our meters and meters will cancel, our per second and seconds. The only remaining unit we have left is the joule. So if I put all this information into the calculator, you will get a value of 3.98 times 10 to the minus 21st joules. But because this is of a single photon, it's actually beneficial for us to say this. So this would be joules per photon. So that would be a correct answer for part A. Let's go look at part B. Now we want to look at a mole of photons, but at a different wavelength. The process is identical until we get to the last step. So let us go and look at our E equals hc over lambda. So notice that I have a wavelength of 5.00 times 10 to the minus 2 nanometers. So if I do the same conversion with 10 to the minus 9th, it becomes 10 to the minus 11th. So I can plug in all of my known values. First off, let's start with our H. So we have 6.63 times 10 to the minus 34th joules times seconds. We will have our constant for the speed of light. So there is 2.998 times 10 to the 8th meters per second. And finally, we are going to put in our wavelength, which would be 5.00 times 10 to the minus 11th meters. So our meters and meters will cancel. Our per second and second, we're left with joules. So now we would get an amount of joules for each individual photon to be 3.98 times 10 to the minus 15th joule per photon. So now you can see that I have about 6 orders of magnitude more energetic photons for example B than A. But now I only have 1 photon. How do I get moles? Well, now we can go back and multiply this by our Avogadro's number. So because photons are on the bottom, we can say that there are 6.022 times 10 to the 23rd photons in 1 mole of photons. So our photon and photons can cancel. And now what we end up getting is joules per mole. This is going to be a very standard unit that you will see when we get to many of our energy chapters, including thermodynamics. So now you will get a value of 2.39 times 10 to the 9th joules per mole. So if you are given 10 photons, or 1,000 photons, or a mole of photons, remember that when you do this calculation, the first part is just joules per individual photon. Then you need to multiply by the number of photons that you have. The second experiment is actually one of the biggest misconceptions in all of general chemistry. This is called the photoelectron effect, and it was actually solved by Einstein in 1905. This is the experiment that Albert Einstein won the Nobel Prize in Physics for. It was not relativity. So, what he determined in this reaction is that light can act in a duality. It has wave nature, which makes sense seeing that it is considered an electromagnetic wave, but it contains some type of particle nature. He calls this particle a photon. This is the first person to use the term photon as a particle. So when we start talking about the wave duality or the wave-particle duality of light, it is because Einstein believed that there is the wave properties and the particle property of our light. So what does this mean? Well, let us look at this incident light coming in and striking our metal. This is going to have some energy. You see that energy here based off of h nu. When it hits this metal, if it has enough energy, it is going to start to eject electrons that are just barely being held on by this metal. If an electron is ejected, it is going to end up having some velocity. So let us talk about this very simply. If there is not enough energy to eject an electron, we are not going to get any kinetic energy. However, if there is enough energy inside of that incident light, that electron is going to be ejected, and using its mass, we can calculate its velocity. So now you can look at it as having mass and velocity. Well, mass and velocity is really momentum. We are now talking about light having enough energy to move a massless body. This is why Einstein could believe that there is a particle nature to our light. So the equation that he used is now seen here. H nu is going to be our incident light coming in, is equal to our kinetic energy plus what is commonly called the work function. The work function is determinate by the metal that we are using. Some metals hold on to their electrons better than others. So if there is a large work function, that means that the metal is going to hold on to those electrons much tighter than a metal that has a low work function. But how does this mean anything to us? Well, as you can see, I've rearranged this equation for better understanding. So notice that we have our h nu. This is our incident light coming in. If we have a low energy light and we try to subtract the work function from that, if we end up with a negative kinetic energy, this means that we will have no electron removed. But if our light coming in has a large enough energy that if we subtract the work function from it, we are going to get a positive kinetic energy. If we get a positive kinetic energy, we have to go back to our physics idea and say 1/2 mv squared is our kinetic energy, and we can now calculate the velocity of those ejected electrons. So as we're looking at the photoelectron effect, you have to look at many different entities. What is the strength of my work function of the metal? How tightly are those electrons being held on by our metal that is going to be irradiated? Also, how strong is our incident light? The stronger the incident light, the more likely we are to have electrons being ejected, and those ejected electrons may have a higher velocity. Let us go and look at this in a quantifiable sense in the next example. So we can see that we are going to use cesium metal. Cesium is one of our alkali metals and might have a very easy ability to lose electrons. So let us go and look at part A. Calculate the minimum frequency of light required to release electrons from this metal. So what does it mean, minimum frequency? Well, typically you are going to hear the terms threshold frequency. Threshold frequency means that this is the minimum frequency that we can put in to get electrons to move. So what does that mean? If we're looking for the minimum frequency or the threshold frequency, this means that our kinetic energy is going to be equal to 0. We don't have any electrons moving yet. So what does that do for us? Well, we can now say that our incident light is equal to our work function, that they are equivalent to each other because we have no kinetic energy. So what we can do is then say that our frequency is equal to our work function divided by our Planck's constant. So if this is the case, we are going to say that our work function, which is 3.42 times 10 to the minus 19th joules, divided by our Planck's constant, which is our 6.63 times 10 to the minus 34th joules times seconds. Our joules and joules will cancel. Notice that I have seconds on the bottom, and I will get a value of 5.16 times 10 to the minus 24th seconds to the minus 1. So what does this mean? If I were to have a frequency shorter than this, I know that I will not have enough energy to remove any electrons. But let's say that I have a frequency higher than this. Maybe it's 6.00 times 10 to the minus 24th hertz. This means that I have just enough energy that when it strikes the electrons, they are going to leave the metal. So let's see what that actually looks like. So let's calculate the kinetic energy of an ejected electron if light of frequency 1.00 times 10 to the 15th seconds is used for irradiating the metal. So notice that our 10 to the 15th is larger than our 10 to the 24th seen here. So what can we do? Well, we're now going to see that when we have our reaction, how can we get our electrons to move? So this means that we are going to have our kinetic energy is equal to our h nu minus the work function. So I can state that I will get 6.63 times 10 to the minus 34th joules times seconds, multiplying that by 1.00 times 10 to the 15th seconds to the minus 1. And we are going to subtract the work function, which is 3.42 times 10 to the minus 19th joules. If I put all of that into the calculator, you will see that I get a kinetic energy of 3.21 times 10 to the minus 19th joules. So what does this mean? Well, remember that our kinetic energy is equal to 1/2 mv squared. So if I look at this, I can have 1/2 mv squared equal to my kinetic energy. So this means that my velocity of an electron is equal to the square root of 2 times my kinetic energy divided by the mass of the electron. So let's go and put all of that into our equation. So if I do that, I will get the square root of 2 times my kinetic energy, which I solved for. So that is going to be 3.21 times 10 to the minus 19th joules. And now what we have here is I need the mass. This must be the mass of an electron because that is the species moving, but it needs to be in kilograms. So if I do that and I look that value up, you would be provided this on an exam, you will get 9.109 times 10 to the minus 31st kilograms as our mass. If I do this math, you will come out to a value for our velocity of 8.40 times 10 to the 5th meters per second. So as you can see, we have a very strong energy light coming in and knocking out an electron. Because its mass is so small, it, with having a lot of energy, is able to go very fast. In this video, we've talked about 2 very important reactions that now set up the importance of things that move very quickly. While they may have mass, they may actually start to work and act like a wave. Things that are very small and start to slow down, they will start to act like a particle. These 2 experiments are going to help us explain electron movement as we get further into this chapter. Have a great day.